Okay, so now let's go for one where we have all kinds of x's and y's mixed together here in this equation. It's x squared minus 2y cubed equals x plus 1. And our job, determine dy dx in terms of y and x. So what we want to do is we want to somehow isolate dy dx to one side of our equation. We're going to actually end up with a derivative that has x's and y's all mixed together. Now again, because we have one y term right here, potentially we could isolate y and check it out. And I might actually ask you to do that and make a comparison. But for our purposes, let's just go through the implicit differentiation method so we can see how it works. So in this case, we have x squared minus 2y cubed equals x plus 1. So we're going to take the derivative equally on the left-hand side with respect to x, and on the right-hand side with respect to x. So we're saying the derivative with respect to x of x squared minus 2y cubed will equal the derivative with respect to x of the quantity x plus 1. Okay, so now in this case, we can think of this just as our derivative of each term individually. The derivative of a sum or difference is the sum or difference of the derivatives. So we're going to take the derivative with respect to x of x squared. We know we're going to get 2x. 2x to the first, well, dx, that would just be 1. So 2x to the first minus 2, we're going to take that constant, times the derivative of y cubed. Now, by the chain rule, right, we're going to think about this one and say to ourselves, if I had the derivative with respect to x of y cubed, by my chain rule, I'm going to end up with 3y squared times the derivative of y with respect to x. So bearing that in mind, when I take my derivative of my term xy, or y to the third, it's 2 times 3y squared times dy dx equals, and then take the derivative with respect to x of x, that's just 1, plus 0, which is the derivative of the constant 1. And now our job right here is to simplify and isolate dy dx somehow. And that's just a bit of algebra at this point, because we're going to take 2x minus 6y squared times dy dx, and only 6y squared is multiplied by dy dx, right? This is the reason why parentheses are important. So I'm going to subtract 2x from both sides. I'm going to end up with negative 6y squared times dy dx is equal to 1 minus 2x. And then I'm going to divide both sides by negative 6y squared. So I will end up with an expression that looks like this. Dy dx is equal to 1 minus 2x divided by negative 6y cubed, y squared, and really, I don't want to do anything else with this negative right here, so maybe I can take care of that negative and rewrite this expression one more time. And I'm going to do that to simplify this thing, so I'm not carrying around extra negatives when I don't need it. I'm going to rewrite this as the negative times 1 minus 2x, so that's 2x minus 1, divided by the quantity 6y squared. And this is how we're going to leave it. When we say determine dy dx in terms of y and x, this is perfectly okay. If we had an xy coordinate of a point on this line, or on this curve, whatever it looks like, we could substitute in that x and y value right now, other than y equals 0, and find a derivative. And that's exactly what we wanted to do.